Okay, sound is working. Sorry for that. So. Could you raise your hand if you can see the screen? Good, seems to work. If anybody is not seeing the screen, raise your hand. I think that would be easier. Then we would use less power and be better for climate change. Good. So let me just. I think everything is fine. That's fine. I just want this to be up front. That's better. Then I have a clock. Good. So the topic then for the next part is to now look at an example for this general framework. And as I said, the general framework obviously is an afterthought after having done a couple of projects, so it may or may not completely apply to what we see now. And the reason why I actually chose these kind of projects or these control experiments in Erasmus PhD project for kind of this seminar and then the tutorial that will come from that is that they are very prototypical cognitive neuroscience, decision neuroscience tasks. So the perceptual choice task that was the motivation for the model that we now discuss is kind of a very typical perceptual decision-making task, and there have been millions, no, not millions, but thousands of studies that use these kind of perceptual decision-making tasks, and they come in various forms. Sometimes you're supposed to distinguish between houses and faces in noise. Then there are, of course, the random dot kinematogram perceptual decision-making tasks, which work a little bit different than these kind of tasks because they provide evidence over time, but nevertheless they are perceptual decision-making tasks. And then there's a fairly basic perceptual decision-making task that taps into actually sensory or internal noise that is the perceptual decision-making aspects of Erasmus perceptual and economic decision-making experiment and project, and this is what we will talk about now. So we consider a prototypical perceptual choice task as has been used many times and is being used many times in cognitive neuroscience. This task works as follows. Participants sit in front of a computer screen, that's a fixation cross, and to the left and to the right of the fixation cross, these patches, which are called Gabor patches, show up. So essentially, this is a sine function in 2D with a Gaussian window. And as you see, one of these patches is a little bit clearer, and the other one here on the right is a little less clear. And this is here then framed in terms of contrast. So this is high contrast, this is low contrast. Although we still, it's kind of actually in psychopy it's something called visibility. In any case, let's call it contrast, and we will call it contrast throughout. And the idea is that the participant has to decide whether which one has the higher contrast, and then if, for example, in this case has the higher contrast, the participant presses the left button. If it would be the other way around, the participant presses the right button. And of course, there are different levels of contrast difference. So this is a relatively easy trial where it's clearly visible that this has higher contrast than this. But there are also harder trials where both of them essentially look a little bit like this. So if the difference is very small, and then it's quite hard. And that is the task. And there's a decision-making task which has been studied in perception and decision-making in cognitive neuroscience quite a lot. Hauke Heeckeren is famous for discovering the brain area that does perceptual decision-making before he became head of the Corona task force recently. Anyway, that's how things can go. For each participant, we presented the participant with 300 trials in blocks of 25 trials, so 12 blocks. As for Rasmus, this is the Gabor task data, not the perceptual control task, but we treat it here as a purely perceptual choice task. In this sense, it's a control task. And the probability on each trial for the contrast to be higher on the left or the right is equal. So you cannot predict from trial to trial what's going on. The respective contrast differences are uniformly distributed between 0, where there's essentially no difference where there's no difference in the contrast, and quite arbitrary value here, 0.08, which is essentially a contrast difference where everybody gets it always right. Yeah. Do you have questions about the task? Because I think it's a little bit essential that you understand the task. Doesn't seem to be the case. Nobody raises their hand. Good. Then one thing that we always do, and I think it's also important that we do that, is before we develop and formulate our model and estimate that then based on data and so on, it of course makes sense to look at some what we then call descriptive statistics. So basically summaries of the behavior of the participants that usually correspond to some form of averages. What we have here on the left is the action accuracy, which is defined as the number of correct and valid choices divided by the number of valid choices. And by valid choices, valid actions, I should say. Valid actions, because we observe actions. Valid meaning that sometimes the participants didn't respond in the time window where they're supposed to respond. So some of the 300 trials actually don't have a recorded action. And then, of course, correctness is here defined as follows. If the higher contrast is on the left and the participant presses the left button, then it's correct. If on this trial it would have pressed right, it would be wrong. Yeah? So the question is which patch has the higher contrast, that's then the accuracy. And then on this graph, every dot is a participant. So there were 52 participants, and you can see that some participants are quite good, so they get over 90% on average correct. Nobody gets over 95 as it seems, because there are really hard trials where it's really hard, and there you basically just can guess, which is also an interesting topic in cognitive neuroscience, what happens at these really hard trials, but this is not really the topic here. yeah, you see there's some variation. There's one really bad participant. On average, it's kind of 85%, if I remember correctly. So that's the average, that's the standard deviation. The other thing that is quite typical to look at in these kind of perceptual choice tasks is to look how the participants behave in terms of their correctness. Not their correctness, their probability to press a certain button as a function of the contrast difference. So this is normalized. So minus 0.6 means that the higher contrast is on the right. So there's very low probability that people actually press the left button. Yeah? And if the contrast is 0.6, that means it's high on the left, and that probability, or the estimated probability for participants to press the left button, is quite high. And you see that there is, so it doesn't really go up to accuracy of 1 and not quite to accuracy of 0. So there is a little bit of a error probability even at these very high contrast differences. But then, for example, if you go to contrast differences that are fairly subtle, you see that people are roughly, average of all participants, roughly at 50% correct. Yeah. So what this means is you can also read this as follows: if the contrast is very strong in one direction, people are very much correct. If the contrast then gets less, the contrast difference gets less strong, people go to 50% correct. And then if the contrast reverses, they become correct again. It's called a psychometric function, has been modeled quite a lot, typically by sigmoidal functions. It's fairly standard. And it corresponds to the estimated probability. So that's not really a probability, it's just estimated based on the proportions here of pressing the left button based on the contrast difference. Questions about these summary statistics? Doesn't seem to be the case. These summary statistics are also interesting from the perspective of what we are trying to achieve with our models, because with what we obviously want to do with the models is to generate and predict human behavior. And then the question is, what do we mean by this? So do we mean that our models predict on each and every trial what participants do, or do we mean that this model predicts behavior better than this other model, or what does it mean? And the way I think about it is that we are trying to recreate with our models certain behavioral patterns. We don't, of course, we aim to be quite correct on many trials, but we, of course, allow for slips and errors, so we will not be correct on every trial, but we try to capture certain behavioral patterns. And the behavioral pattern that we are mainly interested in here is, first of all, this kind of level of accuracy and this psychometric function. Yeah? So these are the behavioral patterns that we're trying to capture with our models. These are, and this is also interesting from the perspective of modeling, these are single participants. These 52 participants, the psychometric function and their associated accuracies, and you see that there is some variations. Of course, there's also fewer trials for each participant individually. For example, here, participant 31 was not very good. Rasmus, do you have an explanation for participant 31? Do you know what was going on there?
No, not really. No idea.
Not really. So some are really quite good, so have almost step functions, but some are worse. There's variability, it's normal. So, yeah, just to be, and the reason why I bring this up here is because we will do the model fitting on a participant basis. So of course, in psychology and everywhere, you can use hierarchical models or let's say group models that try to fit the average of what a group of participants did. You can use hierarchical models that allow for participant-to-participant variation. Coming from cognitive neuroscience and cognitive neuroimaging, I'm at least quite used to analyzing each participant individually and then and then looking at the group data under random effects models. It's not necessarily the best, I don't know, it's one way to do it. One other way, of course, is to have one big model for the entire data set and fit that by allowing some between subject variation. It's equivalent. The reason why we are doing this participant by participant modeling, mainly coming from cognitive neuroscience and brain imaging, you have quite a lot of data from each participant, so you it's computational much easier to do that participant per participant. And here, I think it would actually work. I mean, it's not that much data, so one could also use like a full hierarchical model, and maybe that's something to explore in the future. Yeah. In any case, that's why I have the single participants here, and also to show you that there's some variation. So this looks quite nice in terms of group data, but of course, individual levels look different. Good. So that's the motivation, and this is the data that we want to apply the model to. So we want to basically develop a mathematical model that can recreate these behavioral patterns. And then, like you know from SCAN, statistical methods, or data science, I have this holy, not triage, that's something different, this holy trinity of model-based science in my head, which is model formulation, model estimation, and model validation. And this is what I will follow here. So the first thing will be model formulation, and then also simulation to look at its phase validity. After that, we will look at model estimation and validation, and after that, we will look at its application. So first, model formulation. So, and this is then where these general principles then now start to get some content in terms of some mathematical terms. So for this kind of task that we describe here, we actually have a task model, and our models we always describe by these tuples. So you can think of them as tuples like in Python, without necessarily the immutability or something. Well, in a given setting they are immutable, but we can of course change them if we want to. But we just say, okay, it's a tuple, so it's just a set of things, and these set of things then have more specific meaning. And currently, the task model is as follows. So the task model is this calligraphic T here. It has T, the number of block-specific trials. So it's kind of really a task block model. In the learning task, I actually make this more explicit. In the current setting, we could have, and maybe I even will change that, because here we can just take all the trials. So I could just say T denotes the number of trials, and I don't need this block specific in here. This is kind of relating to the other stuff. So just the number of trials. Then as a state, we take that, what is true in the world, namely what we as experimenters know, namely that on each trial, the contrast is either higher on the left or the right. Yeah, so that's the true state of the world. And the true state of the world is defined in this case by us as experimenters, and then the experimental script presenting a higher contrast on the left than on the right if the state is 0, and a higher contrast on the right compared to the left if the state is 1. Yeah? And these are just the 2 task states. And that's in perceptual decision-making tasks, you always have this true state of the world, like in statistics, the true but unknown parameter value. Yeah, it's the same thing. Here we call it state, and it's the thing that is out there and it's true, and it's not necessarily directly known to the participant. And in this case, it's definitely not directly known to the participant, because the whole point is that the participant has to infer what the state is. Then the states here don't capture completely what the participant see, because what is presented, let's say, because what is presented are contrast differences, where these contrast differences are conditional on the state, because multiple contrast differences are associated with, for example, the state left, because it can be very strong on the left or just a little bit less strong on the left as compared to the right. So we have this set of contrast differences, which over both states take on values between minus 0.08 and plus 0.08. And then the task allows the participant to press 2 buttons, namely the left and the right, and these actions are then corresponding to the states. Left higher contrast and left button press are 0, 0. Right higher contrast and right button press are 1, 1. These are the available actions. And these things here, this TSCA, so at least these sets here, so we were already shouted at by one reviewer from CCN who didn't like that we put in the number of trials in the model. You don't need to do that. Anyway, yeah. So these things are structural components. Yeah. So these are just sets. We define them. They're just there. They also happen in the implementation, and the values are the same, but they don't. Yeah, they are kind of the scaffolding of the world, but they don't do anything. And that's different for this probability distribution, as they do something. So the first thing that we have here is the state distribution, which is a probability distribution over these 2 states. It's defined as a Bernoulli distribution with a parameter pi, and this parameter pi is 0.5 throughout. So a specific thing about this state distribution here is that compared to maybe the general form of a Markov decision processes, there are no state dependencies from trial to trial. The states are independent, so it's not that if the higher contrast was on the left, then on the next trial there's a high probability for it again to be on the left. So there were no such dependencies, so it was independence, and we just define the marginal state probability and get the joint probability over all states over the experiment in terms of the product. Yeah, and it's a Bernoulli distribution, so essentially it just means on each trial there's a 0.5 probability that the contrast is higher on the left or the contrast is higher on the right. Yeah, and this ST is the state random variable. The next thing is the probability distribution in the task that determines which actual contrast value is presented, because as I said when I presented the task, given a given state, for example, that the contrast is high on the left, there could be a number of contrast values, strong versus up to weak higher contrast on the left, and these are uniformly distributed. I think fairly correctly they were or completely correctly they were discretely uniform distributed. We assume here that they are continuously uniform distributed, and so I think there were like 120 or something like values, maybe even 32 or so. Ask Rasmus. We assume that it's uniform because otherwise it's just a little bit annoying and it doesn't really make much of a difference at all. Just a second. And this then works as follows. If, oh, that's a typo. Yeah, maybe this is what Jasper wanted to say. It should be CT given ST. Jasper, did you want to say that there's a typo?
Actually not. I didn't see that.
Okay.
Should I wait?
Yeah, maybe. Yeah. And then I don't know what I'm saying. There's a typo. It should be CT given ST. Sorry for that. So this is the correct one. That's also correct. Yeah, Franzi hasn't looked over these slides yet. So what can I do? The way it works is that, and this will come up quite a lot. We use this Bernoulli trick quite a lot because we have these 0 and 1 states. If the state is 0, then this is selected. If the state is 1, then this is selected. And then the contrast is sampled from the uniform distribution under state 1. Under state 0, it's from the uniform distribution on minus 0.08 to 0, and from this uniform distribution on 0 to 0.08 if the state is 1. Good. So Jasper, your question.
Yes, I'm not really familiar with the Bernoulli distribution, and so I didn't really get the p pi, the state distribution. Could you elaborate on this a little bit more, or how I could imagine the Bernoulli distribution?
Yeah, the Bernoulli distribution is just you find it in the statistics for data science fairly early on. So it's just the Bernoulli distribution that can I write here? No, I can't write here. Do I have it somewhere? It actually looks quite a lot like this distribution, only that you here. So if you look at this, and instead of the U, you have the P. Instead of this expression here, you have the P. And instead of this expression, you have the 1 minus P. That means if you so it gives you the probability mass for a random variable that takes on the value 0 and 1. So it's for the coin, the distribution of a coin. If the outcome of the random variable is 1, then the probability is selected. This one is selected, which in this case would be P. If the outcome is 0, this probability would be selected, which would be 1 minus P. And this P is actually set to 0.5. So it's just a 0.5 probability on each trial for the state to be 0 or 1.
Okay.
Yeah. So that's Bernoulli. It's kind of so if you know the model of a fair coin, that's usually a Bernoulli distribution.
Okay. Yeah, then I have an idea.
Yeah. And okay. It takes, in terms of probability mass function, it looks fairly much like this. Only then instead of these longer things, you have just 1 minus P and P there. That's the thing.
Okay.
Yeah.
Thank you.
Good. So that's the task model here. Maybe to further elaborate on this, this is here. It's really as simple as this. This is the Bernoulli distribution here. It's the state distribution. There are 2 possible states, 0 and 1, and the probability for the state at trial t to be 0 is 0.5, and the probability for the state to be 1 at trial t is also 0.5. And this shows the state conditional contrast distribution. So there are 2 lines here, one for the state being 0. So conditional on the state being 0, there's a uniform distribution over the values from minus 0.08 for this contrast difference, and the uniform distribution here has a probability mass that is non-zero, and then it's 0 for the positive contrast differences, because for 0 the higher contrast is on the left. And then it's the other way around for state 1. So here you have the uniform distribution with non-zero probability over the contrast differences that are positive, and it's 0 here where the contrast differences are negative. Yeah, so you have these two step functions, one going in this way, and the other one going this way. Yeah. So these kind of depictions of these distributions, I made them so they sometimes help me to actually get my head around how complex these distributions are and how they work. They don't have really much more information than the formulation on the previous slide, but at least, for example, if you see that and you think a little bit about it, and then also they help, I think, what I also do these kind of graphs for is to validate my implementation, because you type of all of these up and you type this into Python code and so on, and then of course you can simulate, as we will see later, which lets you validate the code, but also just plotting what you did also adds validation. Good. So that was the task model. Now the agent model in this case. Or any more questions regarding the task model? It's just what this task model also just is a kind of mathematized formulation of the task, which often you find in cognitive neuroscience papers. They write something, oh, we used a bandit task, and you don't understand what they did. And if you write it up in terms of this, it's fairly precise, and you have something in your hands if you look into the code that people then use, and you can kind of make sense of their code together with the task model description. This is also why I think it's important. Agent model. So yeah, so essentially was there something? No. I will now describe one. Salome, there was a question.
Salome? Yeah, hi. So I was just wondering, for this example, in the previous slide, so it's action independent, this task model.
Yeah.
For this particular example.
Yeah, that's a good point. Yeah, in this case, it's a good point. There are in this task, there are no explicit rewards, and usually, if you have Markov decision processes, then or certain tasks, then usually some aspects of the task depend on the action of the agent, and you're completely right. So in this case, this typical perceptual decision-making task as it exists in cognitive neuroscience is action independent. It's not a common, so let's say in terms of AI research or MDPs or POMDPs, it's not a typical thing, but these typical perceptual decision-making tasks, they are just like that. It would actually make more sense in a way if they weren't, but and of course you can also have rewarded perceptual decision-making tasks where if you're right you get a reward, so it's action dependent. But a lot of these tasks are actually like this, where whatever you press has no consequences.
Okay. Okay. Yeah, I don't know. Okay.
Although, and this is also not quite right, because in these typical perceptual decision-making tasks, you're encouraged to be as fast and as accurate as possible. So you have this implicit reward thing, and we will actually come to that because we account for this implicit thing, but you don't have it explicitly. That's just how people do these kind of tasks. Yeah.
All right. Yeah. Thank you. Yeah.
Well, but yeah, good point. Okay, then the agent model. Now the agent, we will look at actually some variants of agents because we also want to compare some models. But we start with kind of this kind of grandmother agent that where you can then have special cases of, in a way. Although anyway, you will see what I mean later. So the agent model again is a tuple, and what I incorporate here as a first thing is the task block model or the task model, and I mainly, so there are two ways one can play that. So the what the agent needs from the task is essentially the retinal activation pattern. So there's the contrast on the computer screen, and this, by means of light, is transferred to the participant and evokes some activation in the retina. This activation in the retina is then analyzed by the agent in the participant's head. So what we assume that the agent has access to is not the state, but the contrast difference, because we assume that it can, based on the contrast difference, make some reasoning about the state. And hence, this is why this agent needs certain aspects of the task, and what it specifically needs, it's this contrast difference. So this is why in this case I embed the task block model or the task model in there to allow certain access. One can also, so we also have done that differently in the past by basically giving the agent also this contrast difference as one of its properties, and then copying the contrast from the task into the agent. It's very subtle, but it explains why I here have the task model in the agent. What is in a way more important for the agent and for this whole perceptual decision-making thing is that the agent has a set of observations, and these observations, sorry, did I say they have the access to the contrast difference? Then that maybe was not quite correct. Wait, let me think. We will get to that. Maybe I was confused there for a second. Yeah, it has access in the sense. We will get to that. Sorry, I don't want to get completely random. So the most important thing for the agents are the observations. The observations are real numbers that correspond, if you want, to the. Yeah, sorry. I think I was. Oh, let me just go on. This is where I still need to write this up so that I don't get confused. So the agent has access to the observations, and the observations result from adding noise to the contrast difference. So the agent doesn't know the state, can't access it, and it can't also access directly the contrast difference. It can only access an observation which is conditional on the contrast. So I think what I earlier said with that it has access to the contrast, that didn't make any sense. It has a probability distribution that is conditional on the contrast, but it doesn't, of course, on a given trial, it doesn't have access to the contrast. We will see how it exactly works in a second. So the what the agent definitely also has is a set of agent decisions. So it can decide 0 for deciding the contrast is higher on the left, and 1 for deciding the contrast is higher on the right. And then it has agent's observation likelihood. So it encodes, and in this sense, it has something to do with the contrast. It encodes a probability distribution over observations conditional on a given contrast level. And this observation likelihood is defined as a Gaussian. So it's just a Gaussian which is centered on a given contrast difference and has some variance parameter. And I will show you a depiction of that in a second so that it makes a little bit more sense what this is about. Then it has 3 functions: a belief state function, which turns an observation into a distribution over states by actually using the information of the observation only and averaging, and this is now I get a little bit closer to the contrast, averaging over the different contrasts. So it's a little bit tricky with the contrast. The agent is never really actually doing something with a specific contrast value, but it's also not completely unaware that there are these different contrast values because it's averaging over all possible values. This is, I think, what confused me there. we will see that more closely. It has this belief state function to compute the belief state, and it has phi, which is the valence function, which associates valences with the specific agent decisions, and it has a decision function that, based on the decision valences, returns the agent decision. So let me show you two remarks. First of all, this belief state function, this implements Bayesian inference. So you can also call this a Bayesian observer or a Bayes optimal belief state agent or whatever. I here describe it as a function because a belief. So for each observation, you deterministically get a specific belief state. So it's a function in the deterministic sense. The other thing that already with Zanoni's question came up is that the agent valence function and the decision function, they are chosen for a reason here, namely in that they minimize an expected posterior loss function, which I will show you in a second. So these are first the ingredients, and now a little bit more about the workings of this. So first, the observation distribution. So these are the internal observations of the agent. So think about it as the neural activity in V1, conditional, or the distribution of the activity in primary visual cortex, conditional on a given contrast level in or contrast difference in the external world and the retina. So why I always have the retina in there, if you simulate this, the way it works is that you sample the observation, which is what the agent looks at in its primary visual cortex. But of course, you need to know where to sample that from. And this comes, of course, is sampled. So here from a Gaussian distribution that is centered on a given contrast difference level. And the question is, where is this contrast difference level if you think about the agent? And my story is that this is the retinal activation pattern. In this sense, it's going into the agent, or into the participant, but not into the agent. The agent only sees the observation, but a little bit it gets tipped on or turned on by the contrast difference. Thing is, of course, there are many contrast different values. Basically, you have this uniform distribution here, and then for each of these, the distribution of possible observations is Gaussian. So, for example, if the agent now observes a value here, where the cursor is, then of course the agent can not be quite sure whether this was due to this contrast difference or to this contrast difference. Specifically, and this is where the problem here, it will nevertheless be quite certain that it was the zero state. Here it's a little bit more interesting, because if you have at zero, so if there's no contrast difference, you're not quite certain whether it's from a negative contrast difference or a positive contrast difference. Yeah. So this is the internal noise. This is, in my opinion, this is really what perceptual decision making is about. So perceptual decision making is really about internal noise that makes it hard in perceptual decision making if the evidence is only presented to you sequentially, like in random dot chromatograms. It's a little bit different kind of perceptual decision making. It's actually more a perceptual learning representation question. This is pure sensory noise, internal noise processes that affect your interpretation of the external world, and this is modeled here. One thing that is important is that, of course, how good you will be depends on how broad these kind of noise distributions or these observation distributions are. And these are, of course, dependent on a parameter, which was here chosen for this picture to be 10 to the power of -4. If you make it smaller, then, of course, specifically here, people will be more correct around the turning point between these two contrast levels. If you make it larger, it will become flatter and people get worse. We will also see that. So this is a parameter of the agent, and of course that's also a parameter we're interested in estimating. Yeah. Questions about this right now? Always raise your hand. Now I think it's important that if something is unclear, just raise your hand or turn on your microphone and shout in between, so that you get that things get clear. The next thing then of the agent, besides the things that it contains, so the structural components and the probability distributions, are these functions. And the first important function is the belief state function, which takes an observation. So on each trial, it is assumed that the agent, based on the external contrast, samples an observation and observes that, and then maps this observation into a probabilistic representation of this states. So is the contrast higher left or right? And the way we parameterize that here is as the probability of the state being 0, because if we know the probability of the state being 0, we also know the probability of the state being 1, because that's then just 1 minus the probability of the state given 0, given the current observation. And this belief state we call B, and it depends on two parameters. It depends on the likelihood parameter of the agent, and it depends on this kappa parameter, because as you see here, it's the probability distribution of the state given the observation, not the contrast given the observation, because we want the agent to make a decision about the state. So the agent averages out the contrast values. In this kind of setting, we can actually analytically evaluate the belief state of the agent. And I would jump ahead just briefly to here, where we actually see the belief state of the agent as a function of the observations. The belief state was not defined by us. What we defined was the probability of the state, the probability of the contrast given the state, and the probability of the observation given the contrast. Based on this joint distribution over states, contrast, and observations, we can compute the conditional distribution of the state given an observation by conditioning and integrating out the uniform distribution. And this can be I'm sorry. This is the belief state. I have it together with some other implicit distribution. That's but I think it makes sense to show it here. This is the analytical formula for the belief state. So it involves. So the way we found this is basically by writing down the probability model, the probabilistic model over states, contrast values, and observations, and then conditioning on observation and integrating out the uniform distribution. And then you end up with this formula, which involves the cumulative density function of the Gaussian in various ways. So this we found analytical. There are some derivations involved. These will be included in the tutorial. I will now not explain in detail how we did that, but the point is often you can find analytical formulas for the belief state due to the fact that the probabilistic model that you define is fairly simple. If you cannot find an analytical form, of course, we can always find, at least if we're dealing with discrete probabilities, we can always find just by summing and dividing, we can always find it. and of course, in general, you can also use approximate belief states. So in this case, the analytical solution, an analytical treatment is possible, and so we use this analytical belief state. Good. So, but that's in more general terms, the belief state function maps here the observation of the agent onto the belief state. And what does the agent then do with the belief state? Well, first, it assigns, based on the belief state, it assigns a certain valence to the decisions. Namely, for decision 0, it assigns the valence 0 if the belief state is smaller than 0.5, which means it believes state 0 is state 0 can be that it's, I always get confused if it's one way or the other. Maybe this is always when I want to present these things. I'm certainly at one point not sure. Yesterday I thought it through and was clear about it. So the way it works is it has a belief state, and it believes that the state is, for example, 0. Then it would assign high valence to decision 0. So I think this might be swapped. If it thinks it's if it thinks it's state 1, then it assigns high valence to decision 1. Yeah. So the point here is, although this might be swapped, or I confuse myself right now, I'm not sure. If it just uses the belief state, it believes, okay, there's a high probability that I'm in state 0, so I assign a high valence to making the decision 0. And if I strongly believe it's state 1, I assign a high valence to the decision of saying 1. Why do I assign these valences? Because then in the decision function, I take the decision that maximizes the valence function. So I take the decision with the higher valence. Yeah. So the whole thing, what this is supposed to do here is, if I believe more than 50% that it's state 0, I take the decision that corresponds to state 0. If I believe with higher probability than 50% that it's state 1, then I take the decision that maximizes my valence, and this valence is such that it's higher for decision 1. Yeah. Yeah. The point of this, so this is just expressing this very simple thing that if I believe it's 0 more strongly than I believe it's 1, then I take decision 0. It just represents it as formulas, which are then implemented. So if you look into the code, there are actually if statements, and they might actually be the same or swapped as compared to this here. Why like this? So why should, and this is then the question about the action dependency here, or this question of the reward function. Why is it sensible to take the decision 0 if your belief state has higher probability for 0? I mean, it's fairly intuitive that this makes sense, of course. But what one can show, and this is what I include here, is this perceptual choice policy theory, is that deciding in such a manner minimizes the 0-1 loss function. Might actually also minimize other loss functions, but it definitely minimizes this loss function. Yeah, Alexander. Yeah. Hello? I think you need to turn on your mic. Alexander?
Sorry, I was misclicking. Sorry. So I have no questions with that.
No question.
Nope.
Okay. Good. So the point of deciding this way in terms of this valence and this decision function is that it corresponds to minimizing this 0-1 loss function, and this is what we here model, or what we assume is this agent implicit loss function. So there was not really a loss that people encountered, so they were not really rewarded more or less or something. But we assume that people try to be correct and to kind of give a reason why people, or give any reason why people should follow this kind of valence and decision function that I showed on the previous slide. It's a sensible thing to do if you assume a 0-1 loss function. Yeah. So in this sense, this is some base optimal behavior. So for the statistics for data science people who would actually today have written the exam under normal circumstances, I assume they will know what these loss functions are. This is, if you remember, when we talked about getting point estimators out of Bayesian estimates that we discussed, or Bayesian posterior distributions that we discussed, squared loss functions, 0-1 loss function, and so on. And this is just taken from there to give a reasoning behind these kind of valence and decision functions. Yeah, I will not go over this in detail now. You can then read it in the paper. The important thing that is then added to the task and the agent model is now the behavioral model. And this, as I said, incorporates the task and the agent models, but now adds essentially choice noise or action noise to that by means of this decision conditional action distribution. So the idea is the agent takes a specific decision, for example, 0, and then with a certain probability, we observe the action 0. Or the other way you can say it, the agent takes the decision 0, and with a certain probability, the human then actually presses the button corresponding to 0. Yeah. And how high this probability is depends on a parameter tau. So if this parameter tau is 0, then there is no choice noise, and the decision and the agent decision and the action we observe are always identical. If there's a little bit of choice noise, then there is sometimes a deviation of the action and the decision. And if the parameter is 0.5, then it's essentially the actions we observe are fully random, although the decisions might not be. And the way I do that here is with a Bernoulli distribution over actions, which gets selected depending on the agent decision and is parameterized in terms of this tau parameter. This is where you could also use a softmax, for those who know what softmax things are. The main reasons, so one reason why I'm using Bernoulli here is because I think it's just simpler and the parameter is a lot easier to interpret. Yeah, because it's just a Bernoulli, and then if it's 50-50, it's full noise. If it's 0, it's 0 noise. And the other reason why I'm using Bernoulli here is because you only have these two options. I think it gets a little bit harder if you have multiple choice options. Then, of course, there are generalizations of the Bernoulli, but then I think it's not immediately clear how you should distribute the remaining probability over the other actions. So, for example, if you have 3 actions and then you favor one, and the other ones should have noise, so should they be uniformly distributed, the other ones, or not, and so on. And so there, softmax might actually have some points to be used, because then you have more in line with the action valence. But here, I think Bernoulli is really, it makes things easier because you have a better interpretation of the parameter, you have a nicer parameter space, you have still proper definitions if the parameter is 0, which you don't have for this beta parameter in softmax and so on. So this is why I really like Bernoulli here. And you know that and here, of course, softmax would also be here just modeling action noise and not be exploration. But this is a completely different issue. This was more for the more advanced people. And that's what I said. Yeah. So here again, the whole model framework. So the task has a task state. This is generated on each trial, generates the contrast. This contrast is shown to the participant and drives the distribution of the agent observation, which turns the observation by terms of the belief state function into a belief state. The belief state is then passed through first the valence function and then the decision function to come up with a decision. And the decision is then recorded by us under the addition of action noise. Yeah. Questions? No. Good. Yeah. Jesper, just start talking, or maybe
Hi. Yeah, a question I actually had beforehand at some point when you formulate the task model even. Did you think about, or did you try also to do recursion in the model, like taking as a parameter also like the history of, let's say, difficulty of the last trials or something like this? Was it in discussion, or is it generally not not really usable for this kind of model?
Yeah, no, I think it's a good point, and it goes again into this question about the task, the external versus the internal task model. So what we are doing here, what we mainly do is that we, and also the reason why this is now not really playing a role, is that we inform the participants quite explicitly and veridically about what's actually happening. So we tell them on each trial there's a 50-50 chance that it's higher on the left or on the right. So of course these effects, so kind of carryover effects and so on, might still play a role, and of course can be put in here. If one wants. I mean, this is essentially, so at current, we don't try too much to put in fancy psychological cognitive neuroscience effects, but try to be as basic as possible in order to account for the entire complexity in a clean way. Because as soon as you put in things like that, then of course we would have a learning model, and we would have dependencies, and we would have to account for them. We actually have them in this state action reward continuity learning model. Mainly we don't have them here because, first of all, we told the participants that there are none of these things, and second, because it's simpler. But of course, the general framework doesn't forbid to do that. It would be a different agent model, and then it would be an empirical question whether such an agent model would explain the data better than our current version. So definitely there's never a limit to the model space. So another way we think about this is that by describing quite clearly what the task is, what our models are, and having nice code, we get a little bit away from always doing what the reviewers want, because they can easily think about a new model, and then we can say, yeah, here everything is there, so implement it. Yeah. So if you think that's very important, you have the code, you have the model, just get started. Yeah.
Okay, thank you.
Good. Always feels a little bit like saying goodbye after these questions, and when people turn off, goodbye, but you're still there. Yeah. Good. Yeah, these are the implicit distributions again. So because we're now getting from model formulation actually to model simulation. And this is where these implicit distributions come in again. So the first thing that we already discussed as an implicit distribution was the agent belief state. And we had this analytical form for it, which we derived. I didn't show you in detail how we did that, and this would take definitely too long. But then based on simulating the agent, so by basically simulating the task and the agent, we can then also look at the distribution of belief states and have a histogram estimate from that. And I'm just doing that to validate our analytical derivation. There are other implicit distributions that are mainly interesting from the question of model fit, namely what is mostly important is from the question of modeling the data is the probability of actions given contrast values, because we know the contrast values, that's our experimental manipulation, and we want to later evaluate the log likelihood of an action. So we need the probability of an action given a given contrast value, which is our experimental design variable, if you want. And to get to that, what we actually need first is the distribution of agent decisions given contrast values. Because the distribution of action given agent decisions, of course, just this basically embedding this in a Bernoulli distribution. And here, this is actually Rasmus' analytical work. This, of course, as well, but I started a little bit and helped Rasmus. But this is actually something that I didn't derive myself, but I know that Rasmus did that. And although anyway, there are certain things in the proof that can be approved, because suddenly in the proof something was assumed, but this is now nice and fine, and I know that Rasmus is smiling on his camera right now, so that's fine to say that. Anyway, this is the distribution of the decision given the agent decision given the contrast value. And you see it's a little bit less steep than the belief state, because it has this additional thing of integrating out the contrast value. But what you also see is that the agent decision, and this is also in terms of then later modeling psychometric function, the shape of this analytical form, and of course also our validated histogram, is still sigmoidal. Of course, how sigmoidal it is depends on the perceptual uncertainty parameter. If the perceptual uncertainty parameter is really high, so if they always have very broad tuning curves, then you're almost flat. But thing is, in the limit of very high or low contrast, you will always get to a certainty or a probability of 1. And the additional thing that then is put in is the distribution over actions given contrast differences, where in addition the action noise is accounted for. And then you can see, for example, if you have noise level of 0.1, then even for very high contrast values, you will sometimes do it wrong, because this is even if the agent is always correct, there's still the chance that the action is wrong. So this is kind of pointing out the difference between decisions and actions. And as experimenters, we are of course looking at this, while participants might actually have done, or in the agents in the participants' head might have done that. Again, these distributions all can be derived in this case. In other settings, so if we are working on projects, they are important. So this is now for the people that are currently starting projects. So we will definitely be interested in kind of the decision functions and decision valence functions. If the whole thing is a little bit more complex, we might not be able to derive everything analytically. There's actually something in the real Rasmus project which combines perceptual uncertainty and this, where we might also have the case that it's not analytically tractable, where we then use some numeric integration to get to these distributions. So it can, what I'm trying to say is, the framework always works, but sometimes the analytics might not work. Good. Then in terms of the to play with this model a little bit, I created now a case study model space to compare different things and also to look how these things behave. And then also try to explain the experimental data with that. So a first would be a control model that generates random actions. But the way it generates random actions is it actually has it's doing things quite well, but it's always has a probability of 0.5 to come up with either this or that action, regardless of whether it actually is doing quite well internally. The actions will always be random. This is also one reason for using the Bernoulli here. The main reason also for doing the separation between the agent decision and the observed action, so that these random models can be nicely defined. So that's kind of a control model. It just behaves randomly. Then we have one model where this perception uncertainty parameter, so this tuning parameter of these neurons in V1, if you want, is the free parameter, but there's no action noise, so that parameter is 0. So we have one free parameter. Then the other way around, we have a very low perception uncertainty. So essentially no. So what I really want is no perception uncertainty, but you know it's a Gaussian, so we cannot really set the sigma square to 0. We can just make it very small, and just so basically have a very steep psychometric function, but have a free noise parameter, and then have a model with two free parameters. So basically the perception uncertainty and action noise parameter. What you see here also in terms of, for example, what Lilla's new supervisor, I don't know his first name, so his last name is Ma. What he says in his article, and he's of course right, is that Bayesian models typically don't have many parameters because Bayesian models are usually kind of some optimal ways to do things in general, so you don't need, we will see this actually a lot better in the learning experiment. They describe the best way of doing things without any free parameters. So Bayesian or Bayes optimal parameters, Bayes optimal agents usually don't have many free parameters, and that's what we see here. So phase validity, what do these models actually do, and what do I look at here? So first, like I said, we want to represent the behavioral patterns that we are interested in. And that would be, in first instance, action accuracy, and the other thing would be the psychometric functions. Now, if I simulate these models, if I simulate the P0 model, which again is just a control model with a pure action noise, also full action noise, this always performs at 50%. What you see here actually are simulations from 52 data sets, so 52 participants are 12 blocks for these 0 to 1 parameter model. These are only 10. This is actually under full simulation. So here I also simulate the contrast values and the state values at each trial. I've also already written the version that takes the experimental states and the experimental contrast, and it looks fairly similar because these are the same distributions. I don't have the full actual experiment conditional simulation in here because I haven't quite finished that for the other experiment. In any case, the action accuracy here by our control model is at 0.5. The action accuracy for the perceptual uncertainty parameter model, so where it's only the width of these Gaussians that is manipulated, varies between 1 and 0.5 over this amount of parameter space. So the question is, of course, also which parameter space should I look at? And from doing this, I actually figured that, of course, it's a sensible thing to look at the parameter space that fully creates perfect performance and then goes to almost chance performance. I think this covers then the parameter space quite good. So why should you go somewhere or look at a lot of parameter space where the behavior doesn't change? So this is kind of the dynamic range of the parameter space. And you see that not linearly, but in kind of this sigmoidal form, the accuracy gets smaller as the width of these Gaussian tunings curves of V1 get wider, and then you're basically at chance performance. For the pure action noise model, as you increase the action noise, performance decreases. Of course, here you're very good because you have very high, very low perception uncertainty, so you're fairly certain you have a very small tuning curve. And then finally, if you vary both parameters, the action noise and this perception uncertainty parameter, as you go to worse parameters, of course you get worse. So red is here 50% accuracy, and the best you get here. So that's only in terms of accuracy. In terms of psychometric functions, okay, the control model is not interesting, just 50% all the time. What is interesting is to look at, of course, one can also do that in terms of the theory, to look at the different psychometric functions that are generated by the Gaussian perception uncertainty model, whether it's this action noise model. So the Gaussian perception uncertainty model generates different forms of the sigmoidal function, whereas the action noise model always creates these kind of step functions, and depending on the tau parameter, is further away from 50%. So if it's never making an error, then it's this step function. If it's kind of doing errors and kind of 25%, it's this step function, and this is quite different from this. These psychometric functions, they're not quite nice. As I said, these are just 10 participants, 10 simulated participants. Reason is that the whole fitting takes longer for this and blah, blah, blah. I can tell you later about this if we go to model estimation. Thing is, what I'm trying to do here is to go to parameter space along this diagonal. So the because here, of course, you would have many more psychometric functions that one could potentially plot. So we are going, the black line is here, tau 0 and sigma squared 10 to the power of -6. And then as we go diagonally through that, things get worse, but I think it's a little bit hard to identify a clear pattern here. It's also fewer participants. Thing is, one could also plot the analytical versions of this, and this is something that I'm not quite finished yet. I have done that for the psychometric function, but I still have to work a little bit on that. Good, that was quite long already. My suggestion would be to take a break now, and after that go over the model estimation and validation thing. And I'm not quite sure whether we also want to do the other model today or not, but we can discuss that. So so I would say we take a let's say 10 minutes break or 15 minutes break now. Yeah.